last time, or in the last lecture, uh, we did a few topics, and the very last part of the lecture we spent on looking at the electromagnetic radiation, and we established, or we uh, have said that we can look at the electromagnetic radiation as waves, and that's the common perception of electromagnetic radiation. Electromagnetic waves with frequency and wavelengths, etc., and it shows all the wave properties from diffraction, interference, and different properties. We also said that electromagnetic radiation could be regarded as particles. And we said those particles, each particle is called photon. And each photon carries energy. This energy is Planck's constant times the frequency. And so we can think of the electromagnetic radiation as particles. So there is dual nature for the electromagnetic radiation, waves or particles. Now, the waves are very well established. We know that, by experiments, that there are diffraction patterns when we have electromagnetic radiation. And if we try to experiment with light, which is part of the electromagnetic spectra, we get diffraction, we get interference. So the wave nature of electromagnetic radiation is very well established. One of the very early experiments that has proved that electromagnetic radiation is actually particles was done by, or was interpreted by, Albert Einstein in 1905, and it established the photon concept. So in that experiment, which is called the photoelectric effect, okay, and I will describe the experiment here. What do we mean by the photoelectric effect? The experiment goes like this. Let's assume that we have an evacuated chamber made maybe from glass, which is transparent to light, but it's evacuated, so it's a very low vacuum here. And then we have two conducting plates. One of them, the emitter, because it's connected to the negative side of a battery, and the other one is the collector, because it's connected to the positive side of the battery. And then we have an ammeter, which measures the current. Now, all inside this chamber here is vacuum. So it's evacuated to a very low pressure. And these two plates, conducting plates, are separated from one another. So if we apply a voltage across, let's say any voltage, constant voltage, we don't expect any current to pass between these two electrodes in the dark if there is no radiation or nothing is incident on any of these two plates. Now let's assume that we have a light source. And let's assume that we have a knob on this light source so that we can turn the knob and increase the frequency of the light, or electromagnetic radiation in that sense. So what will happen is, as we shine light on the emitter plate, and as we increase the frequency, after a certain frequency value, we see a current passing on the ammeter. So the current is zero as we turn the light on, but as we turn the frequency of the light on, higher and higher, there will come a frequency so that we see current I. And this is this plot here. You see I, and you see the frequency nu. So as we turn the light on, or as we turn the electromagnetic radiation on, no current until we get to a certain frequency, which we call VTH, meaning V threshold, or the threshold frequency. So what we get here is VTH is what we call the threshold frequency. And this is the frequency at which the current start to be measured in diameter. Okay? And then beyond this frequency, as we increase the frequency, the current starts growing, okay, becomes larger and larger. So even though the two plates are separated, but we see current as we shine light. Okay? So what's the deal here? Now, the way Einstein interpreted this experiment is that as we shine light, light consists of particles. So we have photons. Photons are incident on the plate. So they're incident on the plate. They have energy. Their energy is h nu. That's the energy of light. So there will come a time when h nu, as nu increases, then h nu threshold, okay, will be enough photon energy to make an electron here on the plate to free an electron. So an electron absorbs the energy from the photon, and this energy should be enough energy to free the electron from the photon. So when the threshold voltage frequency is reached, the energy of the photon is h, mu h, and this energy of the photon is exactly equal to the energy needed. Let's call it phi. Let's call it m for metal, phi for metal, exactly equal to the energy needed to free the electron from the metal, because the electron is tied to the metal. So this energy phi m is needed to free the electron from the metal, and therefore the electron becomes free, and here we have positive voltage, so the electron moves to the positive electrode, which is the collector, collects electrons, and therefore we see a current high. That's the only explanation for this experiment. That is, energy is supplied to the electron by the photons. So by explaining this experiment this way, Einstein was able to establish that this light has particles, photons, that give away their energy to the electron. And see that the electron takes all the energy of the photon. So the photon is annihilated, no longer exists. It gives all its energy to the electron. And this electron absorbs the energy of the photon, and then this energy is enough, energy phi m, to make it free from the surface. So this phi m depends on the metal or the surface. And this phi m varies or changes from one surface to another. This phi m is called the work function. Work function of the metal. Okay, so the wave function of the metal is the energy necessary to separate the electron from the metal. So that's the explanation that Einstein puts. So when light shines, okay, on a material surface in an evacuated low pressure tube, electrons are emitted from this surface. The frequency nu and the intensity I of light, the voltage V applied between the emitter and surface, as we see here, and the collector and the material of the emitter can be varied. So this is the experiment, this is the explanation. So now, if we increase the energy of the incident light beyond a frequency VTH, so if we increase it to V, which is larger than VTH, so what will happen? The energy of the photon will be h mu, which is larger than h mu th, right? But this mu th is the necessary energy to free the electron, phi m. So when we go beyond nu th, the excess energy, that is the difference h nu minus phi m, that is the more energy that is given to the electron, more than the energy needed to leave the metal, this becomes kinetic energy for the electron. So it gives the electron more kinetic energy. And this is exactly what this equation is, right? The difference, h nu minus phi m, goes as a kinetic energy, okay? So if there is no loss in energy, then this is actually the maximum kinetic energy that an electron can have, okay? Which is half mv. Here, v is the maximum, v max is the maximum velocity of the electron. So m is the mass and v max are the mass and maximum speed of the electron. So half mv max squared is the maximum kinetic energy of the ejected electron. So phi m is work function, which is the minimum work required to free an electron from the surface. That's what phi m is. So the maximum kinetic energy can be, how do we do an experiment to find the maximum kinetic energy? It's simple. What we could do is we could apply what we call a stopping potential. If we reverse the potential minus and plus and apply a potential Vs, then an electron that is freed from here and has kinetic energy moving in this direction, we can stop it by putting a voltage, reverse voltage like this. We call it the stopping voltage, such that half mv, which is the velocity max squared, okay, so that's the maximum kinetic energy, is exactly equal to the opposing energy from the stopping electric field. Because the electric field is in this direction, therefore it will apply a force on the electron in this direction, and it will try to stop the electron. So that is why it's called the stopping potential. So if you go back here, okay, this maximum kinetic energy can be opposed by a stopping potential. A potential is energy per unit charge. And if we're talking about the electron, then the energy of the charge of the electron is E. So E times Vs is the stopping energy on the electron. So again, this equation can be written as h nu minus phi m equals to the stopping potential times E. So this experiment was done at the beginning of the 1900s, beginning of the past century, and it was explained in 1905 by Einstein, and it proved that light or electromagnetic radiation also is made up of particles, or we can view it as particles. So this is indeed a very important experiment. Let's look at this example on this photoelectric effect. the kinetic energies of photoelectrons. Photoelectrons are the electrons produced by optical radiation or by light. The kinetic energies of photoelectrons range from 0 to 4 times 10 to minus 19 joule. Well, then that means this is maximum kinetic energy. Okay, so this is actually half mv max squared. Okay, so that is what this is. Okay, so this is half mv max, which is the maximum value. Now, why do we say the photoelectrons have zero energy? Because they can be free from the surface, but then even though we say it is vacuum, but we still know that we have some particles. So these particles inside the chamber can collide with the electron and make it lose some of its energy. And so these collisions can be so many so that the final energy of the electron could be zero. So all the energy is lost in collisions. But the maximum energy that an electron can have is this one. So that is when light wavelength is 3000 falls on the surface. What is the stopping potential for this light? So we know that the maximum kinetic energy given to the electron should be equal to E times the stopping potential. So the stopping potential should be equal to half mvx squared over E, but half mvx squared, the maximum kinetic energy is this value here. So it is 4 times 10 to minus 19 joule, which is half mv max squared, divided by 1.6 times 10 to minus 19 coulomb, which is E, the electronic charge. That gives us 2.5 volts. So what we're saying is that if the light, the wavelength of the light incident is 3000 angstroms, and remember we said 1 angstrom is equal to 10 to minus 10 meter. That is a very small unit that we use because we're dealing with very short distances or very short lengths. So that means what we have here is 2.5 volts to stop electron from reaching the collector. Then the next question is, what's the threshold wavelengths for the material? Now again, the threshold wavelengths, we go back and use this formula. Now we know the stopping potential. We know E, the electronic charge. We know what else do we know? Do we know phi m? Okay, we know lambda, right? We know lambda. We want to find phi m. That's the work function. So we know nu, we know h. Why do I say we know nu? Because nu is equal to c over lambda. And we know c, the velocity of light or the speed of light, and we know lambda, therefore we know nu. Okay, and we know Vs, we know E. So we can find phi m equals hc over lambda minus Vs times E. So let us go ahead and put these numbers. This is h, this is c, this is lambda in meters, this is Vs, the stopping potential in volts, this is the electronic charge here, and what we get is phi m equal to this amount, this energy in joules. So to separate an electron from the metal surface, we need this amount in joules, which is very small. Okay? For the threshold frequency is the frequency of the photon that will just match this energy, the work function. Okay? So H nu VTH is equal to phi m. And that is what we had as I was trying to explain to you back here. Okay, so back here I was saying that this HVTH, it should be phi m. Okay, so we go back here and use this equation here, HVTH equals phi m. What do we know? We know phi m, we know H, then we can determine nu TH. So again, nu TH is the same as C over lambda TH, because always the frequency and the wavelengths of radiation are related by the speed of light. So hc over lambda th equals phi m, where lambda th is the threshold wavelength. So we just substitute now. This is h, this is c in meters per second, and this is phi m. And so once we do that, we get lambda th, which is equal to 7.57 times 10 to minus 7 meter. So if we want to change that into angstroms, we multiply by 10 to power 10, because 1 meter is equal to 10 to the power 10 angstrom, and we get 7,570 angstrom as our threshold uh, lambda wavelength. Then the last question, suppose the wavelength of the incident light is increased. Now, you remember, if we increase it to 3,600 angstrom, find the corresponding change in the stopping potential. So now we want to change lambda. Okay, so this is the equation. The stopping potential is equal to times E is equal to hc over lambda times phi m. Phi m is constant. That's the work function of the metal, which is constant. But if we vary lambda, then we also vary Vs. So these are the two. C is constant, H is constant, E is constant. The only variables are V and lambda, Vs and lambda. So we can differentiate, create a differential of this equation. So if we differentiate, we get E dVs, that's the differential of the left-hand part. And if we differentiate here, differentiating 1 over lambda, we get minus lambda squared d lambda. So that's a differential of the second part. Now, if lambda increases from 3,000 angstroms to 3,600 angstrom, then the d lambda is the difference, which is 600 angstroms. Okay, that's our d lambda. Okay, and then lambda is 3,000. That's a starting lambda. H is known. C is known. We can get the increased dVs in the stopping voltage. So dVs is equal to minus H, this is H here, times C divided by E times lambda squared here. Here is d lambda. And what do we get? We get 0.83 volt. That's the increase in Vs. So the new Vs, okay, or it's actually the new Vs should be this is added to it. So the new Vs should be 2.5 times plus 0.83. So you get a higher voltage to stop. Sorry, minus. This is minus. There is a minus sign here. So you get a lower voltage, which is something like 761 volt. So the stopping voltage becomes smaller because when you increase lambda, you decrease the uh, energy of the photon. So that is the solution of this problem. Okay, so now we have looked into the electromagnetic radiation, and we have established that the electromagnetic radiation can be regarded or viewed as waves, but at the same time it could also be viewed as particles. So it has this dual nature. Then the next question that comes to mind immediately, okay, can we do the same thing about particles, objects? Can objects be viewed or looked at as waves? In other words, I'm asking this question, can any one of you, students sitting and listening to me, can myself be a wave? Can a car be a wave? Can we look at any object or particle and think of it as a wave? That was a question that was posed back in 1924 after establishing the dual nature of light. De Broglie was a PhD student at that time, and he's a French prince, by the way, postulated that particles can or should exhibit wave properties. So de Broglie said, oh, we can look at particles as waves too. Particles also have dual nature. They can be looked at as particles, and they could be looked at as waves. So this